Should we wait for 5 more minutes?
Start.
Yeah. Let's start. Is there anything that any questions from the previous lecture? Okay, Diksha, start.
Okay. So in the last lecture, we wrote down the radial Hamiltonian for hydrogen atom, and it was given by, I was denoting it as HL Coulomb. It was given by minus d square by dr square plus L into L plus 1 over r square. This was the angular momentum term, minus 1 over r. This is the Coulomb potential term. And then we wrote down superpotential and we wrote down two supersymmetric Hamiltonian, H1L and H2L, and both were given by H1 of L was given by HL of Coulomb plus 1 by 4 L plus 1 square, and HL of 2 was given by HL plus 1 of Coulomb plus 1 by 4 L plus 1 square. So both H1 and H2 are related to the same system, that is the Coulomb potential system, but at different levels. So H1 is related to the Coulomb potential at angular momentum L, angular momentum quantum number L, and H2 is related to the angular momentum quantum number L plus 1. Okay. And then we found the ground state. Which is annihilated by H1 of L. So I assume that only H1 of L has the zero energy state, because I showed last time that only one of the two Hamiltonians can have zero energy state, and I assume that this is H1 in this case, and we found the state which is annihilated by H1 of L, and I represented it as U0 of L, because L is this quantum number, because H1 is labeled by L, and U0 means it's the zero energy state. So this was this, and we explicitly found the wave function. So we explicitly solved the equation, and we noticed that solving for this equation was easier than solving for the full Coulomb potential, because the full Coulomb potential is a second order equation in differential equation in R, but H1 is a first order differential equation. But if you solve for H1 of L at 0, you just have to solve for A of L. I'm not writing A and A dagger again. You just have to solve for A of L acting on U is 0, and this is a first order differential equation. Since this was a first order differential equation, we solved for this equation, and we found the ground state wave function U0 of L, and we also found, since H1 of L acting on U0 of L is 0, from this equation, let me call it equation 1, from 1 we get HL Coulomb acting on U0 of L is minus 1 over 4 L plus 1 square U0. So this is the lowest energy state of Coulomb potential at level L. Notice that this energy is negative, so the energy being negative implies this is a bound state. So as you know, for the hydrogen atom, this is the first bound state. So the energy goes as 1 by n square. I will show why this is n. Okay. So now let's try to find a state which is annihilated by H1 of L plus 1. So initially we found a state annihilated by H1 of L. Now instead of finding a state annihilated by H1 of L, I'm finding a state annihilated by H1 of L plus 1. It will become more clear why I'm considering this. So I'm trying to find a state such that H1 of L plus 1 acting on that state. That state I call it U0, since it's again the ground state. It's again the ground state, but of the Hamiltonian at L plus 1. So U0 of L plus 1 is 0. I'm trying to find this state. Now notice that H2 is related to H coulomb at L plus 1 from this equation. And I can substitute H coulomb at L plus 1 from equation 1 here. So you will see that H2 is related to H1 at L plus 1. This I'm not writing the equation again. I'm just saying that H2 of L can be expressed in terms of H1 of L plus 1. Just by noticing these two equations. Because if you change L plus 1 here, this will be H1 of L plus 1 and then you substitute it here. So H1 of L plus 1 I can write in terms of H2 of L. What I will get? HL of 2 minus 1 over 4 L plus 1 square plus 1 over 4 L plus 2 square. This is H1. This whole thing is H1 of L plus 1. This I wrote down by noticing that H2 and H1 both are related to H coulomb. This acting on U0 of L plus 1 is 0. So this implies that HL of 2 acting on U0 of L plus 1 is 1 by 4 L plus 1 square minus 1 by 4 L plus 2 square U0 of L plus 1. So now we have found, what we found that U0 of L plus 1 is eigenstate of HL of 2. Now remember the diagram from yesterday. So if this is H1, this is H2. What we had seen that the ground state is not paired. So the ground state of H1 of L, this is L, I'm taking it L. The ground state of H1 of L was U0 of L. So this is not paired with anything. But then we found that U0 of L plus 1 is some finite energy state. So this energy is some E L plus 1. This energy is this 1 by 4 L plus 1 square minus 1 by 4 L plus 2 square. So this is some finite energy state of H2 of L. But now we know that this state should be related to some state in H1 by just applying A dagger L operator. Because the non-zero energy states are paired in both Hamiltonians H1 and H2. This we know. So hence, now this procedure is simple. We will find the first excited state of H1, which I call it first excited state at level L. So the first excited state at level L will be related to this state by applying A dagger. So applying A dagger L on U0 of L plus 1, I will get this state. Is this step clear? Are there any questions?
Ma'am?
Yes.
Ma'am, isn't it that we just found that H2 of L has a eigenstate U0 L plus 1, but these are not really proof that it is a ground state of H2L?
Yeah, okay. Even if it's okay, so you want to know whether this is the minimum energy state of H2 of L. This is the
Right.
question.
Because then it
No,
will correspond to the fast excited state. Otherwise, it will not correspond to the fast excited state.
okay. No, but because why it is the ground state? Because if instead of u0 of L plus 1, if you took any other L, if you took L plus 2 or any other L, then the L will appear here. That energy will increase because it will increase the quantum number in the denominator. So that will have more energy than this state. So this is basically the lowest energy state that you will get. And now
Right.
this should be related to, since it is paired, it has to be related to some state in the H1. But it cannot be paired to the zero energy state in H1 because the zero energy states are not paired.
Right.
Hence, it is related to the first excited state. Because this is just because we
Yeah,
can
yeah.
see
Diksha,
that
1
L
minute.
appears in the denominator.
Debojyoti, can you please mute and can you please unmute when you speak? Yeah, okay. Thank you. Yes, Diksha, please.
Sorry. So the point is when since L appears in denominator here, if you increase this L, the energy is going to increase. So this is the minimum one for HL of 2. So this is the lowest energy state of HL of 2. And now it has to be paired with some state in H1. It cannot be paired with the 0, 1. It's paired with the first excited state. Is it clear?
Yes, ma'am.
Okay. So now let's see what is the energy of U1 of L under H1. So H1 of L.
Sorry, I have a question.
Yes.
Yeah, so wait a minute.
Okay.
Hello, Arindam.
Hello, sorry, can you hear me?
Yeah.
Yeah, sorry. So the ground state of H1L plus 1.
H1 L plus 1. Okay, yes.
Hello.
Yes.
So the ground state of H1L plus 1, are you saying that that's the first excited state of H1L?
H2L. Sorry, H1L. Yeah. This is the first excited state of H1L after applying a dagger operator.
Yeah, but how do I see that? I mean,
because H1 of L plus 1 is related to H2 of L. This you can see from here. From the second
that's
equation.
right. Yes.
From the second equation, if you substitute HL plus 1 of Coulomb from the first equation to the second, what you will see here, H1 of L plus 1 will appear.
Right.
So H2, so what from here, what you will find that H2 of L is related to H1 of L plus 1.
Yes.
So by finding the ground state of H2 of L plus 1, you can find the, sorry, H1 of L plus 1, you can find the eigenstate of H2 of L.
Yes.
Now, from supersymmetry, we know that the eigenstates of H2 of L are related to the eigenstates of H1 of L by applying a dagger operator.
Right,
so to
right,
this
right.
state, you apply a dagger L to get some state which will be the first excited state of H1 of L. So this basically tells you that H1 of L and H1 of L plus 1 are related.
That's right. Yeah,
Their states are
thank you.
related by applying a dagger operator. I will make a diagram probably at the end again so that it becomes more clear. Okay. Any other questions? Okay. So let's see what is the energy of this state U1 of, I am claiming that this is the first excited state of H1 of L. Let's see if this is actually the case, if this is actually the related to, if it is actually the eigenstate of H1 of L. So I'm applying H1 of L on U1 of L. This is basically, what is H1 of L? Is A of A dagger of L, A of L, and acting on U1 of L. This I can write as A dagger of L, A of L acting on A dagger L of U0 L plus 1. Now, this A dagger is basically H2. A dagger. Remember H1 was A dagger A, H1 of L, so L L. H2 of L was AL A dagger L. So this AL A dagger L is H2 at level L, acting on U0 L plus 1. Now we already saw that H2 acting on U0 of L plus 1, H2 acting on U0 of L plus 1 is this. So this is A dagger of L acting on 1 over 4 L plus 1 square minus 1 over 4 L plus 2 square on U0 of L plus 1. So this A dagger is here. So you will basically, sorry. So what you will get is 1 over 4 L plus 1 square minus 1 over 4 L plus 2 square acting on U1 of, because A dagger on this is U1 of L. So H1 of L acting on U1 of L is giving you this energy. Notice that this energy is more than the energy you got for U0. Okay, I haven't written that equation. Okay, now let's see what is the energy of this thing under H coulomb. H coulomb of L acting on U1 of L. Now, remember the relation between H coulomb of L and H1 of L is, what is the relation? H1 of L minus, from this, H1 of L minus 1 by 4 L plus 1 whole square minus 1 by 4 L plus 1 whole square on U1 of L. Now, H1 of L acting on U1 of L, you also already know from here. This 1 by 4 L plus 1 square cancel. So what you will get is 1 minus 1 by 4 L plus 2 whole square. So what you found? You found the state U0 of L initially. This was eigenstate of H coulomb of L with the energy minus 1 by 4 L plus 1 square. Then you found another state U1 of L, which under HL of coulomb had energy minus 1 over 4 L plus 2 square. Okay. And I can explain the thing in the mass. I can write it again. So what was the thing? So U0 of L was eigenstate of H1 of L and also of H coulomb of L. The energy under this eigenstate was 0, but the energy under H1 of L was minus 1 over 4 L plus 1 square. Then what you found that U0 of L plus 1, which is zero energy state of H1 of L plus 1. This is zero energy under H1 of L plus 1, but under H2 of L, this is again eigenstate of H2 of L also, but under H2 of L, its energy was 1 by 4 L plus 1 square minus 1 by 4 L plus 2 square. This is about the state U0 of L plus 1. Then you applied A dagger L on this operator. So you got U1 of L, which was A dagger L acting on U0 of L plus 1. This new state U1 of L is now eigenstate of H1 of L with eigenvalue 1 by 4 L plus 1, because H1 and H2 are paired. So they have the same eigenvalue, with the eigenvalue this. And it's also eigenstate of H coulomb of L, now with the eigenvalue 1 by minus 1 by 4 L plus 2 square. So these are the three states we have looked at till now. Is this clear? Okay. So now what we have seen, that by applying A dagger L operator on the ground states of H1 of L, H1, you can get first excited state, and now similarly you can get higher and higher excited state by applying A dagger operators. So by induction, what will you get? You will get a state which is U nu of, so U0 of L under HL coulomb had eigenvalue minus 1 over 4 L plus 1 square. U1 of L under H coulomb had eigenvalue minus 1 by 4 L plus 2 square. Similarly, if you keep on doing this, applying this A dagger, but you will find a state at level nu of L will have eigenvalue under H coulomb given by minus 1 by 4 L plus nu plus 1. Here it was, sorry, yeah. With L, for the 0, it had just L plus 1. For 1, it has L plus 2. For nu, it will have L plus nu plus 1. Just by induction, you can see that. And now let me define a new quantum number. Let me define a new quantum number. Number n, which is equal to L plus nu plus 1. And you know, since nu is greater than equal to 0, this implies L is greater than equal to n minus, sorry, is less than equal to n minus 1. This is basically the principal quantum number of the hydrogen atom. So in terms of nu, what will you get? The energy En is given by minus 1 over 4 n square. If you remember, this is the energy of the hydrogen atom. It goes as 1 by n square. It just depends on the principal quantum number n, and the L quantum number takes value from 0 to n minus 1. Okay. So hence, so in the similar way, by applying A dagger operators, we can find the whole spectrum. So let me just summarize again what we have found. So now here I am plotting this. So this is the energy level E. This I'm writing, I'm taking L is equals to 0 state, then L equal to 1, L is equals to 2. So L is equals to 0 state will have the lowest ground state will be U0, and now I'm putting L also 0. I was representing as U0 comma L, now L is also 0. For L equal to 1, the state will be U0, the lowest energy state will be U0 but 1. And now we saw that if I apply A dagger L, now L is 1. So if I apply A dagger 1, I will get the first excited state of L minus 1. So I will get U1 of 0. Similarly, if I start with U1 of 1 and I apply A dagger 1 on it, I will get U2 of 0. And this U1 of 1 you can find by starting from U0 of 2 by applying A dagger 2. So this way you can find the full spectrum of the hydrogen atom. Is it clear?
Also the wave functions, right?
Yeah, also the wave function. This I just found the energy. The wave function you just find by solving this equation. So the wave function sorry, there is the wave function. So the wave function U0 of L plus 1, this wave function, since it's the zero energy state of H1 of L, this wave function you can just find by solving the equation A acting on L plus 1, A of L plus 1 acting on U L plus 1 is 0. And this is first order differential equation in R. So you can solve this to find U0 of L plus 1. So similarly, you can find the ground state wave function, and then applying A dagger on them, you can find the higher wave functions. Is it clear? Okay. So, okay, as an exercise, if you want to understand more about this procedure, you can, as an exercise, you can try to solve for this superpotential. If the superpotential is minus L plus 1 over X plus X. This will give you, if you apply, this will give you Hamiltonian of isotropic harmonic oscillator. The thing Shivankada was asking last time. So basically this will give you 1 by R square minus 1 by R square plus, sorry, 1 by R square plus R square type of potential. Okay. This example, all these examples are there in the notes. I shared a link with the last lecture. So all these examples are there in those MIT notes. Okay. Any question?
Yes, I have a question. Can we have more than one superpotential for a given system?
Well, for a given system, can you have more than one superpotential? So to find the superpotential, given a potential v of x, you remember we had a differential equation. So there was some number here plus some number here, w square of x. You're saying if this equation can have more than one solution. But
Yes.
since it's a differential equation, if you, I don't think it can have, since there is a square term, it might have. I don't know any example in which they have, but in principle, if there are multiple solutions to this equation, you can have. But I don't know
Okay.
if you are asking any example, I don't know any example where this happens.
Okay.
Yeah, I mean, I have a claim actually.
Yeah.
Claim is that except for 1 over r and r square, maybe you cannot find this w. That's my claim.
Okay. No, I don't know. Another was saying last time, no, that for every super integrable system, you can find such superpotential.
What I'm telling, using this equation, using these two equations, I mean, sorry, using this form, w prime and w prime plus w square.
Yeah.
Okay. So if I go to, so okay, just a minute. So if I go to spherical polar coordinate system, then this L plus 1 by r square term will be there. That is the centrifugal part. Okay.
Yes.
And then the potential will come from whatever potential you had originally.
Yes.
So my claim is that if Vr is 1 over r, then of course you can get whatever you have done. You can also find W for Vr equals to r square. Actually, I mean,
Yes.
I couldn't find any. I took some r to the power n. Okay,
Yes.
Vr equals to r to the power n, and I don't think whatever I looked at, it didn't seem that I will have some W of r which will consistently give me.
So, okay, so Shubhankar, let me understand. So, you're saying in 3 dimensions,
Yes,
apart
in
from r square and 1 over r, you cannot put it in supersymmetric form. That's your claim.
I think yes. I think that is my claim.
Okay. Actually, most of the examples I
It
know.
is consistent because I think these are the only 2 super integrable system as far as I know in 3 dimensions.
Okay.
But
Okay.
I don't know a way to prove or disprove your thing actually. Yeah.
No, I mean, I can tell you, and not just I mean, not by words. If we meet sometime, I can tell you why I am telling that. If you just take v equals to r to the power n, okay, and you
Yes.
take your w to be some a alpha n r to the power n running from 1 to 0 to, sorry, minus infinity to plus infinity, okay, something like that, and then you plug it, and then you try to figure out if you can find these alpha n's. What
I see. I see.
what it turns out to me that if n equals to minus 1 and 2, I can consistently find alpha n's.
I see.
If it is not, then I mean, if I want to match with something, then I will generate some other term which is not in Vx, and all these possibilities are happening.
I see.
Okay.
I see. Yeah.
Okay.
Okay. Okay. Yeah. You just assumed a form of Vx and you plug the
Right,
general
right.
form
I
of
just
W
took
and
the
try to
form of
find the
Vf.
solution.
Yes, exactly.
Yeah.
But Shubhankar, the what? So if I understand, you just assume that V is some r to the power n. What
Right.
about if I assume V is also sum over some r to the power n's, something like that? Then
Infinite.
something. I mean, even if it's infinite, let's say.
Infinite, then I don't know.
Yeah, for cosecant and all, if V is like cosecant x or something, for some of the trigonometric functions, you can find superpotentials. There are certain examples. Uh, so if you have a series such that it's a
But
trigonometric
Diksha,
function,
in that case, we actually do not have this centrifugal term.
yeah, yeah. Oh,
Yeah.
you are talking more about 3D. So 1 by r square
Yes,
is
yes,
already there.
yes, yes,
Okay, okay,
yes,
okay,
yes.
okay, okay.
No, I mean what? Okay, okay. Let me get Shubhankar. So you are saying that if the potential has some finite number of terms in terms of polynomial expansion, then these are the only 2 things. Is that the claim?
Yes. Yes.
Okay. Okay, that's still a
now I do not know. I mean, if you say your potential is also some beta n r to the power n, where n running from minus infinity to plus infinity, that I do not, that I haven't checked. I just
No,
took
that
some r to the power n.
that thing we have to think very carefully about the boundedness and infinity.
Exactly.
Yes.
If your potential, I mean, if you maybe probably you can take some some finite number of Laura terms. I mean that 1 over some r to the power of some 1 over r to the power some n, and n should have a lower limit. I'm not sure whether you can take n to infinity, because then you will have some essential singularity at r equals to 0.
Yes.
Okay, okay. But I just found one paper, interesting paper, which claims, I have not read and I have not tried to prove it myself, that apparently in one dimension, any potential can be embedded into supersymmetric system. Which is
Can you
different
share
from
the
what you
link
are
in the
saying.
chat?
You are studying 3D, so that paper claims any 1D potential can be embedded into supersymmetric.
Can you share the link in the chat?
Yes, I can. Yes.
Yeah, but for one day, I think the thing is you can, yeah, you can always write down a superpotential solving this, because there is no, you don't have to worry about only one term. But whether that will make the system easy to solve or not is, you cannot say,
Yeah.
because
That's certainly a different thing. I don't think that does, but the claim is that any 1D. That's also consistent, Diksha, because any 1D Hamiltonian system is integrable, and also, I mean, tautologically it's super
yeah,
integrable.
yeah.
So okay, I will share the link. Yeah, but please continue. Okay.
Okay. Okay, now I'm moving to a bit different topic. So I'm moving to Lagrangian formalism. Okay. So, so let me define quantum mechanics in a bit mathematical way. So quantum mechanics, you can think of quantum mechanics as basically 0 plus 1 dimensional QFT, quantum field theory. Let me tell you why. So in quantum field theory, any field phi is a function of space-time coordinates xi and time, where I runs from 1 to 3 in 4D. So this system I call it a three spatial dimensions plus 1 time. So this system I call as 3 plus 1D QFT. And now if my fields phi depended just on time, then I say that there is no I, there is just T, so it is just 0 plus 1 dimensional QFT. So there is 0 spatial dimension and there is 1 time. And now when you write down the Lagrangian, so what is a Lagrangian? So Lagrangian, let's say for the free particle. So for the free particle, what is the Lagrangian? Lagrangian is just half d phi of t by dt, d phi of t by dt. Where this phi of t is telling you about the trajectory of the particle, of this particle. So what is phi? Phi is basically a map from R, in this case, to again R. Why I'm saying R? So what do you mean by phi is a map from R to R? Meaning that phi, so this R is my time t. So phi, so phi is basically a function of a variable t, which takes value in real numbers. So phi is a function of variable t which takes value in real number. And when you plug in a t, the quantity that you get, phi of t, is again a real quantity. So I'm taking a real field phi. So it's phi is basically a function from t, from r to another r, and this the coordinates of this r. So this r is parameterized by time t, and this r is parameterized by phi of t. So usually when you talk about this, you call this as the base space. So you call phi as a function from some base space to some target space. where in this Lagrangian above, the base space is R, is a real line which is parameterized by by time t, and the target space is again a real line R which is parameterized by phi of t. For example, in 3 plus 1d q of t, what happens in 3 plus 1d? My base space, since my phi depends on xi's and t, so my base space is R4. More precisely, it's R3, 1, because there are three. Because in your metric you have one minus signature and other three are plus, so it's Lorentzian. So R3, so this is the base space, and again, if phi is a real field, the target space is again R. So for the 3 plus 1d system, your function phi is a map from R3, 1 to R. Okay. So in general, when you write down a Lagrangian, which basically is a function from some R, from some space to another space, you call this Lagrangian as a sigma model Lagrangian. This is just a definition of sigma model. Okay. Okay. So let me write down a more generalized Lagrangian. So a more generalized Lagrangian I will write down is half. Let's say I have n fields phi. So I represent phi as phi I, and I takes value from 1 to n. So I have n scalar fields phi. So now the kinetic term, there can be mixing in the kinetic term. So there will be a metric Gij d phi I over dt d phi j over dt. This is my Lagrangian. Now in this case, my phi's, phi i's are a map from R, because again they just depend on t, but now to some manifold M whose metric is given by Gij, and the coordinates are your phi I. Is it clear, or I'm making things very mathematical?
Maybe Diksha, you take one particular example like S3 or something and tell this.
Taking Gij.
Because some of them haven't had a GR course, so they may get bit confused.
No. For my case, for whatever I will do, I will take this manifold M to be just Rn, to be just flat. So Gij I will take is delta Ij, which is a flat metric. So for my case, all the example that I will consider will be the simplest one, which is half d phi I over dt d phi I over dt. So it's just a flat metric. Basically, this Lagrangian, you can write it in let's say this thing. If I write the Lagrangian in terms of the matrix, so I have let's say I have two fields phi 1 and phi 2. Let's say I have two fields phi 1 and phi 2, and my Lagrangian is like half d phi 1 by dt d phi 1 by dt plus half d phi 1 by dt, sorry, d phi 2 by dt. So I have a mixing term between phi 1 and phi 2, and let me just put one, and then plus half d phi 2 by dt d phi 2 by dt. I can write this I can write this as this matrix, no? I can write here there is half, here there is again half, half, half. This is d phi 1 by dt d phi 1 by dt. Sorry.
Second one is d phi 2 by dt.
Sorry, d phi 2 by dt d phi 1 by dt d phi 2 by dt. So I can write my Lagrangian as this, no? So if I multiply these three matrices, I will get this. So this is basically my matrix Gij. This is my matrix Gij. These are my fields phi 1 and phi 2 are my fields. So the Lagrangian in terms of the matrix I write as half Gij, where this is Einstein summation notation actually. If you have not done GR course, maybe you also don't know. When I write it in this way, this means there is a sum over I and then there is a sum over j. And I and j both run from 1 to 2. So this thing will have 4 terms. G11, d phi1, d phi by dt, d phi1 by dt, plus G12, d phi1 by dt. So, and this is my G11, this is G12, this is G21, this is G22. So when I write the Lagrangian as this, when I was writing as just half Gij d phi I over dt, d phi j over dt, whenever the indices are contracted, it means there is a sum over those indices. This is called Einstein summation notation. So when I was writing the Lagrangian here, so the I index is contracted. This means there is a sum over I. The j index is also contracted. There is a up index and down. There is a sum over j. Here, when I write as I, this means I index is contracted. So this Lagrangian, if I had only two fields, this Lagrangian I will write as d phi1 by dt, d phi1 by dt. This is I is 1, and then when I is 2, then this will be this. So this is the Lagrangian. So usually, so this is the so if I write the Lagrangian as half Gij d phi I by dt, d phi j by dt, this means my phi i's are a map from R, which is parameterized by T, to some other manifold M, which is parameterized by metric Gij, and the coordinates of that metric are phi I, phi x. Is it clear? Any questions? Okay. Okay. So for my purpose for today, what I will take, I will take my my matrix Gij to be just a flat metric delta ij, which basically means there are no cross terms like this. So this term is 0. So if I have n fields, so if I have n fields, phi I, so I is from 1 to n, the Lagrangian is just half. Okay, I'm writing d phi I by dt as phi dot. Okay, this is my notation. So this will be Lagrangian will be half phi dot square, phi1 dot square, plus half phi2 dot square, plus up to so on half phi n dot square, which I can, using Einstein summation notation, I will write as half phi I dot phi I dot. This means there is a sum over I. So this is my bosonic Lagrangian, because phi, I'm considering it as a scalar field. What do you mean by a scalar field? Scalar field means under the Lorentz transformation, it is invariant. So any field, you characterize it as scalar field, spinor field, spin half field, spin 1 field, spin 2 field, depending on how it transforms under Lorentz transformations. Okay. So if my field is invariant under Lorentz transformation, it's a scalar field. So this is my bosonic Lagrangian, half phi I square, phi I square. Okay. And now, in order to supersymmetrize the system, I need to write down a fermionic Lagrangian also. So since you have done a course on QFT, the first fermionic Lagrangian you might have known is basically Dirac Lagrangian. So Dirac Lagrangian, let me again write it is with the, if I have psi I, which are my fields, which are my Dirac spinors. And I is again from 1 to n. So I can write down the Lagrangian Gij by 2 psi I d slash psi j, and I and j and again contracted. This is the Dirac Lagrangian you might have seen, you know this, no? In QFT. So this is in QFT. And also you might remember that there is another index on the spinor. There is another index on this spinor, which is alpha, which is the spinor index. Do you guys know these things or not? Okay.
Speak up now. He's asking.
I think this is fine. I think they know these things.
Ah, okay. 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 So now, so this was in QFT. So where D slash, what was D slash? Gamma mu, D mu. If you remember, D slash is usually gamma mu, D mu, and gamma mu are your polymatrices. And what polymetrics obey? They obey this algebra. That the commutator between gamma mu, gamma nu is, for my notation, I'm taking -2 G mu nu. If you have done QFT course with Arnabda, he usually takes this notation, so I'm sticking to that. Okay. Now remember, so where mu was your 0, 1, 2, 3 for the 3 plus 1D QFT. Now I am in quantum mechanics. So in quantum mechanics, I just have time. So this is
Diksha,
0 plus 1D
is it eta mu nu? Is it eta mu nu? Gamma nu? Or you want to keep it G mu nu?
Okay, let me take it as Himenu. I don't want to introduce flat indices, the spinner the VLY indices. So for me, usually it's G mu nu and the gamma
Yeah.
A, gamma B is flat. But because I will work with the flat space,
I
let me
don't
take it
think
as
they are familiar with these real lines. So maybe just keep it to eta mu nu. It would be.
yeah, okay. So I'm just keeping it Himenu. Okay. So for the 0 plus 1D system, mu is just 0, no? I just have time. I don't have any spatial coordinates. So my D slash will be gamma 0, D0. Where D0 is, what is D0? D0 is d by dt. Now from here, if I take my metric, usually I don't know I don't know if you take eta 00 to be plus or eta 00 to be minus. Okay. So from here, the metric I am taking the notation that gamma 0 square from this algebra. What I will find, gamma 0 square is -1. Because this, when mu and nu both are 0 and 0, you will get 2 gamma 0 square is equals to 2 eta 00, 2 and 2 cancels. And I take eta 00 to be 1. So I get gamma 0 square to be 0. So gamma 0 for me is I. I can take gamma 0 to be I. So my D slash is I d by dt. I'm just doing all this to motivate what is the fermionic Lagrangian in quantum mechanics. Because I know you have done the Dirac equation, so that's why I'm writing it in this way. So my fermionic Lagrangian for quantum mechanical system then is, okay, I by 2. So whether this is I or 1, this depends on the conventions. So in my conventions, this is this. You might look at some other book where the conventions are different. So gamma 0 people could have taken to be 1 or to be some other thing. So in my convention, this is the case. And I'm taking Gij, psi I alpha. I have to first d by dt. So dt psi j alpha. So this is the fermionic Lagrangian. Okay. I'm taking the so for bosons, since I took Gij to be delta Ij, I'll do the same for fermions. So Gij will be my delta Ij. So my Lagrangian for the fermion is 1 by 2 psi alpha I psi dot alpha I. The dot, where with psi dot I mean dt of psi. And what is this alpha? So alpha is the spinor index. So let me count the number of degrees of freedom. So okay, let me count the degrees of freedom. Then since I will take the fermion psi to be real, so psi bar and psi will be same. So I'm first counting the degrees of freedom to tell. There is alpha, no? So just to tell how many degrees of freedom there are, and when I take psi to be real, you will just get psi I. So psi bar will basically be equal to.
Yeah.
Or are you saying that there should be a psi bar here, so there will be one more gamma 0? because psi bar is psi dagger gamma 0, no? Were you talking about this? That here, usually in Dirac, but it just depends on the notation, because I could have taken. Okay, so let me count the. So let me count the degrees of freedom first. So in general, this is something I will not prove. I'm just stating the statement. In general, a d-dimensional fermion, d-dimensional Dirac fermion. Okay. Do you guys know the difference between Dirac fermion, Majorana fermion, and Weil fermion? Can anyone just unmute and say yes or no?
Maybe not all of them know, but some of them yes.
Some of them may know, yeah.
Okay. Okay. So I will consider Dirac fermion. Dirac fermion is something which obeys this Dirac equation, d slash psi is equals to 0. So that is my definition of the Dirac fermion. So in general, and generally you apply some extra conditions on fermions, and when you apply some extra condition on top of this d slash psi is equals to 0, you get either Majorana fermion or the Weil fermion. But I will not go into those things. So I'm just taking a Dirac fermion. So a Dirac. So in D dimensions, a Dirac fermion has 2 power d by 2 complex degrees of freedom. So number of degrees of freedom of a Dirac fermion is given by this, where this square bracket means greatest integer less than or equal to. So if my d is 1, since I was in a 0 plus 1d system, so my d is 1, I have, and the greatest integer less than or equal to half is 0. So for one, so in 1d, so in basically quantum mechanics, Dirac fermion has 2 power 0, which is 1 complex degree of freedom. Okay. Okay. What else I wanted to say here? Yeah, if you don't know this, check for 4D. 4D, you know, Dirac fermion has 4 components. And if you check this, you will get that there are 4 complex degrees of freedom. So this is the statement is. So there is one complex degree of freedom. This implies 2 real degrees of freedom. So when I was writing psi I alpha, my alpha is 1, 2, where psi I1 and psi I2 are the 2 real degrees of freedom of my Dirac fermion in 0 plus 1d. That is in quantum mechanics. So when I write this, there is implicitly a sum over alpha. So this is psi I1, psi dot I1, 1 or 2, whatever, psi I1, psi I2, and then there is a sum over alpha. So for my case, for the case of least supersymmetry, for the case of least number of least supersymmetry in quantum mechanics, since I took that is 1 real supercharge, I will consider a system with 1 real fermionic degree of freedom. So I will demand that my psi I alpha is real. So psi I alpha dagger, which Shivankara was saying that it should be there in the Lagrangian. So this I demand it to be psi I alpha. In other words, what it means to say is that my psi I1 is equals to psi I2, which is basically I'm writing as square root of 2 psi I. So I will not write the spinor indexes alpha and 1 and 2 now from now on. This condition is called Majorana condition. So now I am taking a Majorana fermion. So what is a Majorana fermion? Basically, it's a Dirac fermion plus it obeys above condition. So it has less above condition. Above condition. So it has less number of degrees of freedom than Dirac fermion. Okay. So what have we done till now? I took a Lagrangian of a boson and I took this boson to be real. Boson real. So I have one real bosonic degree of freedom. And then to this Lagrangian, I can add, to supersymmetrize the system, I can add LF, which is a fermion. But I take this fermion to also be real. So I have one real fermionic degree of freedom. And this whole system, this total system L, will be my supersymmetric system. And it is, since it's supersymmetric system, both bosonic and fermionic degrees of freedom match. So I did this counting just to tell you that I want to consider a system in which the fermionic and bosonic system, the degrees of freedom of fermion and boson match. Since my boson was real, so it had only 1 degree of freedom, I have to consider a fermion which is real and only 1 degree of freedom. So this is my SUSY Lagrangian. So L SUSY in quantum mechanics, and what is my supersymmetric Lagrangian now is half d phi I by dt d phi I by dt. Okay, I'm saying one, so each boson has one real degree of freedom. Since I took n bosons, so there are n bosonic degrees of freedom, because I runs from n1 to n. So there are n bosonic degrees of freedom. And similarly, I took n fermions, so there are n fermionic degrees of freedom. Plus I by 2 psi I d psi I by dt. So this is my Lagrangian. So this is my supersymmetric Lagrangian. This system is usually called n is equals to half supersymmetric system, because when people do the counting, people take one complex supercharge to be n is equals to 1 SUSY. Since I took one real supercharge, this is called n is equals to half SUSY. So what is the supersymmetry transformations now? So you can check that this system is invariant under these following. If you do this these transformation, delta phi I is equals to I times epsilon psi I, and delta psi I is minus epsilon phi dot I. If you do these transformations, now this epsilon, since so this delta is the SUSY transformation. SUSY transformation. Since SUSY transformation is a fermionic, supersymmetry is a fermionic symmetry, so this epsilon is a Grassmann parameter. So Grassmann parameter meaning that when it crosses any Grassmann number, it will give you a negative sign. And notice that since psi is a fermion, these psi's are Grassmann. For fermion, you have so these psi's are also Grassmann. So since these psi's are also Grassmann, this epsilon is also Grassmann. The anti-commutator of psi and epsilon. So sorry. So you get psi epsilon is minus epsilon psi. So when you change the order, there is a negative sign because this is epsilon. Why this is supersymmetry transformation? Because it's taking a boson. So phi was a boson to a fermion. So it's taking a boson to a fermion, and vice versa. It's taking a fermion psi to a boson. So phi dot. So you can check that the above Lagrangian L, so L, SUSY, or in particular, you can check that the action, which is integral of dt of L, is invariant under above transformations. And my epsilon is a real Grassmann parameter. Since there is only one epsilon, so I have only one real supercharge. And hence I have n equal to half SUSY. Any questions, or was I going too fast? Okay. So once you do these variations, let me just complete by doing the variations. I'm running out of time. So if I do the SUSY variation, delta of S.
What was the supercharge here?
Yeah, that is what I am writing now.
Okay.
I will write the Noether charge now.
Okay.
So if you do delta S, what you will find, it's basically a total time derivative. So it's basically dt of something. And by Stokes' theorem, you will find that this is 0. This is an exercise. So it's like a homework problem. Given above transformations, find delta S and show that it's 0. Now, if you have done, so now you can compute the Noether charge corresponding to above transformations. Charge for above transformations. So this is also a homework. Compute the Noether charge. And you will find the Noether charge. I am representing the Noether charge by Q. You will find epsilon times Q. So you will find Q epsilon times Q to be minus epsilon square root of 2 psi I x dot I. And this is the supercharge. So your supercharge Q. So the Noether charge corresponding to this symmetry is called supercharge. And the supercharge is basically psi I x dot I. This you will find. Okay, I can stop here. Any questions? Okay, let me tell one. Sorry. Did someone say something? Okay, let me tell you one more thing which I forgot to mention.
Is that pi instead of x?
Oh, sorry, 5. Sorry, yeah. I don't know. Did I use x somewhere else also? No. Okay. So I talk when I talked about so I talked about base space and target space. And in the case above, my base space is just R parameterized by T, and the target space was Rn parameterized by coordinates phi I. It was n dimensional because I took value from 1 to n. Now notice that this phi I, these are scalars. If you talk from the perspective, if you do Lorentz transformation in T, Lorentz transformation, there is only one variable. So Lorentz transformation will be just like a translation in T. These are scalars here. But on target space, these are vectors. Why these are vectors? Because they have this vector index I. So if you do any transformations on the target space, then they transform as vectors. But if you do any transformation on T variable, so if you change T, then phi I of T transform, and if you change T, so phi I of T will be equal to phi I prime of T prime. This is how a scalar transform, no? If you change T. So if you transform the variable T, if you do transformation on variable T, that is on base space, it transforms as a scalar. But if you do transformation on the target space, that is if I do rotation, if I rotate phi's, that is phi I going to some rotation matrix Rij phi j. So this transformation phi I transformed like a vector, because this Rij are the function of phi's, are function of the target space. And similarly, this psi I alpha, they were fermions from the perspective of the base space. So if you change T, they transform as a fermion. But they again have a vector index I. So if you do transformation in the target space, they transform again as vectors. I don't know if this will be this is not useful required to do the things I will do now next, but I'm stating this because this is a very general concept that appears in string theory and all when you do worldsheet. So there's a notion of a base space, and then there's a notion of a target space. Base space is the quantity on which your fields depend. So for 3 plus 1D thing, your base space is R3, 1. For quantum mechanics, your base space is just R. You can, for string theory, your base space will be two-dimensional. So it's just usually it depends on two variables T, sigma. And the target space is the space where the fields take value. And the way the fields transform in base space is different from the way they transform in the target space. I'm just mentioning this for people who are more curious about this notation, base space and target space notation. Okay. Any questions?
Ma'am, what exactly does it mean for phi to be in base space? Because phi is a map from base space to target space, right? So phi in base space and phi in target space, what would it mean? Like,
no, I'm not saying in base space. Sorry, maybe I used wrong words. Phi, as you said, is a map from target space to base space. But so phi is a function of t. So if you do a transformation on t variable on the base space, then the value of phi that you will get is similar to what you will get for a scalar. So basically, it transforms like this. And for a fermion, you will get some other spinner thing. And but if you change phi itself, so if you do a transformation on the target space, that is basically changing phi itself. It transforms as a vector. So as you said, phi is not in base space. It's a map from base space to target space.
okay, ma'am. Thank you.
Well, it's a map from base space to target space, and hence finally it changes as per target space change, right? So it finally leaves on the target space.
Yes. Yes. The target space coordinates are phi I. So phi's values of phi live on this Rn, live in this space.
I mean, just one comment. All of you who have not done this should try to do at least this supersymmetry checking. You will understand why it is complicated, because when you do first time, you always miss a minus sign and your answer will not match.
Yeah. Also, these variations I wrote down from my old notes. So you might find that there is a minus sign mistake in this. So please do check this delta S, whether delta S is actually 0 if you take these variations or not. I checked yesterday that I think the signs are correct, but there might be a mistake. So please try to do this. Okay. Okay, then we can stop here. So when should be the last lecture?
Tomorrow and Thursday is not good, so it will be on Friday.
No, Friday is not good either.
Okay, then.
What is the problem tomorrow?